Pluto's orbit has consistently presented potential entanglements. Its path crosses that of another planet, which has raised concerns since its discovery. Pluto, a small and mysterious planet situated at the farthest reaches of our solar system, has become a subject of significant interest in recent astronomical discussions. Recent reports suggest a potential collision with Neptune, raising alarms within the scientific community and among space enthusiasts. Notable scientists such as Neil deGrasse Tyson and Michio Kaku have voiced their concerns about the potential repercussions of such an event. But what has led Pluto to be on a collision course with Neptune? And what might this cosmic showdown mean for Earth? Join us as we delve into the details of this potential cosmic conflict and explore why astronomers are worried about this rare celestial behavior. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet primarily due to the peculiarities of its orbit. Despite this reclassification, Pluto continues to fascinate and capture the imagination of astronomers and space enthusiasts alike. Recent statements from experts like Neil deGrasse Tyson and Michio Kaku suggest that Pluto's orbit could cross Neptune's path, raising the possibility of a dangerous collision with significant implications for our planet. Pluto's journey around the Sun is remarkable due to its unique characteristics. Its orbit is incredibly long, requiring a staggering 248 years to complete one full revolution. Since its discovery in 1930, Pluto has yet to complete a single orbit around the Sun. What makes Pluto even more intriguing is the highly elliptical shape of its orbit, which contrasts sharply with the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at a 17 degrees angle relative to the ecliptic plane, resulting in a much steeper path compared to the orbits of other planets. This combination of orbital inclination and elongated shape complicates Pluto's motion, making its path unique. An intriguing feature of Pluto's orbit is that it repeatedly intersects Neptune's orbit every 248 years. At these points, Pluto's path brings it closer to the Sun than Neptune, defying the usual assumptions about the positions of planets in the solar system. Further analysis reveals that Pluto's orbit is far from a perfect circle. Instead, it follows an elliptical or oval trajectory, causing its distance from the Sun to vary significantly. At its closest, Pluto comes within approximately 30 astronomical units, AU, of the Sun, but at its farthest, it stretches to more than 49 Australian dollars, nearly twice Neptune's average distance from the Sun. Moreover, Pluto's orbit is inclined at an angle relative to the other planets, further complicating its interactions with Neptune. This inclination is crucial in understanding how Pluto and Neptune interact. When their orbits cross, the gravitational forces between the two bodies influence each other, gradually altering their respective trajectories. This dynamic relationship highlights the interconnected nature of the solar system, where the gravitational pull of one planet can affect the movement of another. Thanks to advancements in technology and improved observational instruments, astronomers have been able to track Pluto's movement with increasing precision. This has allowed for a clearer understanding of its orbit and the potential effects it may have on the overall stability of the outer solar system. While the likelihood of a direct collision between Pluto and Neptune is low, the possibility is actively studied, as the consequences of such an impact could be catastrophic. Despite Pluto's small size and distant location, it continues to captivate scientists and space enthusiasts alike. A central question remains: why hasn't Pluto collided with Neptune already? The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been working to understand its peculiar orbit. Unlike most planets, which follow relatively consistent paths along the ecliptic plane, Pluto's orbit is distinct due to its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit has remained remarkably stable, showcasing the intricate forces at play within the solar system. The study of how Pluto, Neptune, and the Sun interact presents a significant challenge for astronomers. Predicting their movements requires a deep understanding of the gravitational forces that influence each other's paths. To solve this cosmic puzzle, scientists rely on several specific conditions, including apsidal libration, scope libration, and VSOP oscillation. For instance, apsidal libration plays a crucial role in maintaining the stability of planetary orbits. When Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, ensuring that a direct collision does not occur. Scope libration ensures that Pluto stays positioned above Neptune's path when it approaches, reducing the likelihood of a collision. The VSOP oscillation, named after scientists von Zeipel, Stevens, and Kaplan, explains why Pluto's orbit appears odd yet remains stable over long periods. Although space may seem chaotic, there are underlying patterns that prevent Pluto from colliding with Neptune or significantly altering its trajectory. The concept of orbital chaos describes how a celestial body's path is highly sensitive to its initial position. Even minor changes in Pluto's starting position or velocity can have significant effects over long periods. To model Pluto's interactions with Neptune and other celestial bodies, scientists use advanced simulations. These simulations explore the potential outcomes of even the smallest shifts in Pluto's course. In the late 1980s, these simulations revealed a fascinating result. Despite Pluto's seemingly stable orbit, it can still behave unpredictably. A slight change in Pluto's position or speed could lead to dramatic changes in its orbit over time. However, even with these uncertainties, Pluto's orbit has remained stable for billions of years, suggesting that, despite its erratic motion, it follows an underlying order. The eccentricity of planetary orbits, such as Pluto's, makes it difficult to predict long-term changes with certainty. These models require highly precise initial conditions, as even small errors in the data can lead to vastly different outcomes, making accurate predictions incredibly challenging. Understanding Pluto's orbit is particularly important when considering a future collision with Neptune. This knowledge contributes to a broader understanding of how our solar system operates. Pluto's orbit serves as a prime example of the unpredictable nature of space. Unlike the orbits of other planets, Pluto's path is highly elliptical, leading to unusual encounters with Neptune. This erratic movement makes it challenging to predict the system's long-term behavior. However, gravitational forces play a critical role in preventing Pluto and Neptune from colliding. Gravity, the force that pulls objects toward each other, ensures that, despite their overlapping orbits, the two bodies remain apart most of the time. The time these gravitational cooperations exhibit the sensitive equilibrium of powers that oversee space, an immediate crash between Pluto and Neptune remains impossible. Such an occasion would have huge ramifications for our understanding of the planetary system. The release of energy from such an event would be enormous, and the debris dissipated across space could have far-reaching effects, potentially affecting other planets and moons. Neptune's orbit itself could be altered, further complicating the dynamics of the outer planetary system. As space exploration continues to advance, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Scientists continue to study Pluto's trajectory to better understand how large planets influence its motion. This knowledge is essential for understanding the intricate relationships between celestial bodies and how their movements might affect one another. Despite the rare nature of Pluto's orbit, some of the world's foremost scientists, like Neil deGrasse Tyson, have hypothesized that Pluto could eventually collide with Neptune. Tyson, a renowned astrophysicist, considers Pluto's reclassification as a dwarf planet a significant step and emphasizes the need for continued exploration. He believes that Pluto's eccentric orbit highlights how much remains undiscovered about space and the forces that govern it. According to Tyson, the mysteries of space make studying it so compelling, and he urges others to explore the fascinating complexities of celestial mechanics. Tyson, along with other experts, expresses concern over the potential dangers posed by Pluto's unusual trajectory. If a collision were to occur, it could have catastrophic consequences for the planetary system. The release of energy from such an impact would be massive, and the debris scattered throughout space might affect other planets and moons, potentially altering their orbits. Theoretical physicist Michio Kaku, known for his work in string theory, also offers valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is crucial for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that analyzing Pluto's interactions with Neptune could help guide future space missions and improve safety in space exploration. Kaku also highlights the importance of understanding gravitational forces in the context of space exploration, as these forces could shape the future of how we explore distant planets. His work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could provide valuable data that would contribute to our understanding of gravity and spacetime, central concepts in string theory. While a collision between Pluto and Neptune would likely not directly impact Earth, it could offer a unique opportunity to study the behavior of fundamental forces under extreme conditions. As scientists continue to explore the far reaches of space, the unpredictable nature of planetary interactions becomes more apparent. Studying celestial dynamics, such as the gravitational relationship between Pluto and Neptune, provides valuable insights into the fundamental laws of the universe. By continuing to observe and study these phenomena, we are drawing closer to understanding the vast and complex nature of the universe. The gravitational interaction between Pluto and Neptune highlights how even distant planets can influence one another. These celestial bodies exert gravitational forces that subtly shape their orbits over long periods. While the likelihood of a direct collision remains low, the possibility is not entirely ruled out, keeping scientists interested in monitoring the situation. They believe that by understanding these forces, they may one day be able to predict and mitigate the risks associated with such cosmic events. An intriguing aspect of planetary motion is how seemingly random interactions can lead to stable and predictable patterns. This is evident in Pluto's orbit, which may appear irregular but is actually governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of various planets and Pluto's orbit ensures that the dwarf planet follows a steady yet complex course. Understanding this intricate relationship is key to advancing our knowledge of the broader solar system. As scientists continue to study Pluto's orbit, they also look toward other areas of space exploration. For example, studying systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances. In some cases, this can increase the likelihood of a planet's orbit becoming unstable. Though the TRAPPIST-1 system is not currently facing any collisions, scientists remain cautious, tracking the movement of planets in these crowded environments to better understand the risks and how they might evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, which wander through space unbound to any star. Rogue planets, which travel through space unattached to any star, present an entirely new set of challenges for astronomers. These planets, not bound by the gravitational pull of a star, drift freely across the galaxy, making their orbits unpredictable and difficult to track. Unlike the planets in our solar system, which are influenced by the Sun's gravity and follow relatively stable orbits, rogue planets can be subject to the gravitational influence of passing stars or other celestial bodies, significantly altering their paths. While rogue planets are a relatively new area of study, their behavior offers valuable insights into the dynamics of planetary motion and gravitational interactions on a much larger scale. The discovery and study of rogue planets could help astronomers refine their understanding of planetary formation and the forces that shape the orbits of planets within solar systems. These free-floating planets do not conform to the usual rules of solar system dynamics, so studying them could reveal new aspects of how planets interact with one another, as well as how planets can form and evolve without the presence of a host star. This information could also provide clues about the potential for life on planets that do not orbit stars, a question that has intrigued scientists for decades. Rogue planets might offer a unique opportunity to study the effects of gravitational interactions in isolated environments. With no star to anchor them, these planets rely on the gravitational forces of nearby objects to influence their motion. This makes them a fascinating subject for exploring the potential effects of gravitational forces in more chaotic, less predictable circumstances than we see within our solar system. Understanding rogue planets could also contribute to the broader field of space exploration. If we are to explore other star systems and potentially colonize planets, the study of rogue planets and their trajectories may play a key role in predicting their behavior and identifying any potential dangers. Examining rogue planets could also help us design spacecraft that can navigate complex gravitational environments, including those involving wandering planetary bodies.